Hi there, Mr. Sutton here. Thanks for joining us for the BC Calculus 617 Extra Practice Number 4 Solutions on Euler's Method. On this problem, we're being asked to use Euler's Method with increments of 0.1 to approximate basically f of 1.3 given f of 1 equaling 0 in this differential equation here. So in order to do this, we're going to start by figuring out what f of 1.1 is, and then we'll move on with 3 steps to get to 1.3. So f of 1.1, that's going to be f of 1, which they gave us, that's our launching off point for all of this, plus f prime of 1 times our step of 0.1. F of 1 they told us was 0. F prime of 1, we're going to have to use this differential equation here. So plugging in the x value 1, I have 2 times that x value minus the y value that goes with 1. So that's the y value 0 that they gave us here. So we have minus 0, which doesn't make a difference, but it's the principle of the matter, I guess. And this comes out to 2. So we have 0 plus 2 over here times 0.1. This is really just 0.2 when all is said and done. And we move on now to find f of 1.2. So that's going to be f of 1.1 approximately, plus f prime of 1.1 times 0.1. F of 1.1 we said was about 0.2. And again, I'm writing the approximately equals at this point because this is already an approximation. For f prime of 1.1, we now have the x value 1.1. So I'm going to be doing 2 times 1.1. Minus the y value that we just found goes with that. That's this y value we just found here of 0.2. So this is 2.2 minus 0.2, which is just 2. So we've got 0.2 plus 2 times 0.1. And then this is 0.2 plus 0.2, which comes out to 0.4. All right, well, we have one more step to go. We have to find f of 1.3. That's actually what we were trying to do. But you got to take it one step at a time on these Euler problems. So this is f of 1.2 plus f prime of 1.2 plus our actually times our step size, which is still 0.1. So now we have 0.4. That was what f of 1.2 was that we just found. For f prime of 1.2, now we have 2 times the x value 1.2 minus that y value that we just found of 0.4. So this is 2.4 minus 0.4, which is still 2. It's kind of interesting how that works out the same each time. I kind of wonder if it would do that if we just kept going. I don't know. We're not going to keep going. So we have a plus 2 over here times 0.1. This is 2.2, or actually just 0.2, plus 0.4, which comes out to 0.6. For this one, we're using Euler's method with increments of 0.1 to approximate f of 1.2, and we're given f of 1, so that means we're going to have to take 2 steps if we're going by 0.1 to get to 1.2. So let's start by finding f of 1.1. That's going to be f of 1 plus f prime of 1 times our step size of 0.1. So that's going to be 2 plus whatever f prime of 1 is. To find f prime of 1, we have to plug in the x value 1 for the x in this differential equation. But we also have to plug in the y value that goes with that x value. So we've got 2 minus the x value 1, and that comes out to 1. So we have 1 times 0.1 over here. So this is really 2 plus 0.1, which is 2.1. Now we go on to f of 1.2, which is actually what we were trying to find all along. So that's going to be f of 1.1 plus f prime of 1.1 times 0.1. F of 1.1 was approximately 2.1. We just found that. F prime of 1.1, well, that's going to be the y value 2.1 that we just found minus the x value 1.1 that we're now plugging in. So this just comes out to 1. So we've got a plus 1 times 0.1 over here. This is 2.1 plus 0.1, which comes out to 2.2. So that's our approximation for f of 1.2. For this problem, we have this differential equation, 1 plus y. We're given f of 2 equals 0. And we basically want to figure out f of 1.7 using Euler's method and increments of negative 0.1. So to get from 2 to 1.7 using these increments, we're going to have to go 3 steps with Euler's. Our first step is going to be to figure out f of 1.9, and then we'll just keep working our way backwards. So f of 1.9 then, that's going to be f of 2 plus f prime of 2 times our step of negative 0.1. F of 2 they actually gave us, that was 0. F prime of 2, to find that we have to use this differential equation. Now notice that this only takes y values, so when I do f prime of 2, I'm really just plugging in the y value that goes with 2, and that's the y value 0 here. So this is just 1 plus 0, and then that's just 1. So back over here we have 1 times negative 0.1, which just comes out to negative 0.1 when you add it to that 0 over there. Okay, so let's keep going. F of 1.8, we're working our way back, 0.1 at a time. This is going to be f of 1.9 plus f prime of 1.9 times our step of negative 0.1. F of 1.9 we saw was approximately negative 0.1. F prime of 1.9, that's now going to be 1 plus the y value that we just found, this negative 0.1 here. So that comes out to 0.9. So we have 0.9 times negative 0.1. That's negative 0.09. So negative 9 hundredths. And here we have this negative 0.1 here already. So that's negative 0.19. And we keep going. It's getting a little trickier though with those decimals. So we have f of 1.7. That's as far as we need to go. That's going to be f of 1.8 plus f prime of 1.8 times negative 0.1. F of 1.8 we saw was negative 0.19. And then that's going to be, let's see, f prime of 1.8 is going to be 1 minus this y value right here. Well, actually 1 plus this y value, but it's negative, so we have minus 0.19. This comes out to, let's see here, 0.81. So we've got 0.81 times negative 0.1. And this is going to be all sorts of fun here. This is negative 0.081. And we already have a negative 0.19. So that's all going to come out to negative 0.271, I believe. Yes, there we go. Got it. So that's our approximation. For this one, we're told y equals f of x is the solution to this differential equation, 3x plus 2y. We have the initial condition f of 1 equals 0.5, and we want to approximate f of 1.2 using Euler's, starting at 1 with 2 steps of size 0.1. So really nothing is left to the imagination on this one. They just tell you exactly what they want. So using Euler's, in order to get from f of 1 to f of 1.2, we need to go 0.1 at a time. We're going to start by finding f of 1.1. That's going to be f of 1 plus f prime of 1 times the step size they told us of 0.1. So f of 1 they said was 0.5. F prime of 1, we're going to have to use this differential equation. So we have 3 times the x value 1 plus 2 times the y value that goes with the x value 1. So that's this y value over here of 0.5. So 2 times that. This is going to be 3 plus 1 when all is said and done, so that's 4. So we have 0.5 plus 4 times 0.1. Basically 0.5 plus 0.4, which is 0.9. And we're going to simplify as we go because we're going to have to match one of these answer choices, and it is a no calculator question. So the good news is we only have one more step. We just have to find f of 1.2 itself now. But for that, we needed to know f of 1.1, which we just found. We also have to add f prime of 1.1 times 0.1. F of 1.1, again, that was the 0.9 that we just approximated. F prime of 1.1, that's going to be 3 times the x value, 1.1, plus 2 times the y value that goes with this x value. So that's this y value right here, 0.9, that we just found. So we've got 3.3 plus 1.8. That's 5.1 altogether. So that's our f prime now. We're adding that times 0.1. And we're just going to have to be careful doing this out now. This is going to be 0.51 plus 0.9. That's going to be, let's see here, 1.41 when all is said and done. So that's going to be answer choice D. For this problem, y equals g of x is the solution to this differential equation, 1 minus y. We have an initial condition of g of 1.5 equals negative 1. We want to approximate g of 0 using Euler's, starting at 1.5 with 3 steps. If I'm going from 1.5 to 0 in 3 steps, that means I have to be going by negative 0.5s on each one. So my first step, I'm going to have to figure out g of 1, because that's negative 0.5 more than, or actually 0.5 lower, I guess, than 1.5. So that's going to be g of 1.5 plus, and this is approximation now, so this is all going to be approximately equal, plus we've got g prime of 1.5 times our step of negative 0.5. G of 1.5 is exactly negative 1, so that's not an approximation. Now this derivative over here, g prime of 1.5, that's using this differential equation. When I plug in the x value 1.5, I'm really plugging in the y value negative 1. So this is really going to be 1 minus negative 1, because this takes y values, not x values. So this is 1 plus 1, which is 2. And then, so g prime of 1.5 we said was 2. We still have that negative 0.5 step going on. So this is really negative 1 minus 1, which comes out to negative 2. And now we have 2 more steps to go. The next step, we have to do g of 0.5. We're just working our way towards 0, 0.5 at a time. This is going to be g of 1 plus g prime of 1 times our step of negative 0.5. G of 1 we just found was approximately negative 2, so now I'm going to be writing approximately instead of equals, because this is not the true y value, this is an approximation. And g prime of 1, that's going to be 1 minus the y value that we just found of negative 2. Now again, since this negative 2 is an approximation, I'm going to write approximately equals over here, not equals like I wrote up here. So this is going to be 1 plus 2, which is 3. So we have negative 2 plus 3 times negative 0.5. This is really negative 2 minus 1.5, which is negative 3.5. And we have to keep simplifying as we go, because we have to match one of these answer choices, and it's a no calculator problem. So we might as well make our life as easy as it can be. Finally, we're going to do g of 0. Final boss battle. This is going to be g of 0.5, which we just found, plus g prime of 0.5 times negative 0.5. G of 0.5 we just saw was negative 3.5, approximately. G prime of 0.5, that's 1 minus the y value that we just found of 3.5. So that's going to be 4.5 when all is said and done. And we're doing 4.5 times negative 0.5 here. That's going to be, let's see here, negative 2.25 plus negative 3.5. That comes out to negative 5.75, which is going to give us answer choice A.